In general, in a CMOS circuit, what is the expression that's normally used for the power? CV squared F, right? So usually the way that it is expressed is there is some alpha which is a switching activity factor, C which is the total capacitance that is being switched, the total load capacitance in the circuit, V is the operating voltage, we have V squared, and F is the operating frequency. Okay. So over here alpha is a switching activity which is essentially architecture or application dependent. What I mean by this is, if I come up with a slightly different way of doing addition, I may be able to reduce the number of times that a particular wire will need to switch. Okay. In general, what happens is that in a large circuit you can expect that at any given clock cycle, roughly 10 to 20% of the wires are going to switch their values from 0 to 1 or 1 to 0. And a fundamental thing as far as CMOS circuits is concerned is the predominant consumption of power happens only when there is actually switching activity, when a given wire is switching from 0 to 1 or from 1 to 0. Okay. Some current is required in order to charge that output capacitance or discharge it, and that causes a dissipation of power, of energy. Okay. C over here is the load capacitance, which depends on A, the total number of circuit elements that are present, and B, the size of the individual circuit elements themselves. Okay. V is the operating voltage, usually VDD, the supply voltage, and F is the operating frequency. Now, in the case of a parallel implementation, if you think about it, effectively speaking, what is going to happen is, as we saw in this diagram over here, the internal frequency at which the adders and multipliers need to switch or need to operate has become half, okay, which is good news. It looks as though there is straight away a power reduction. The problem is it's not as simple as that, because the capacitance, because I have doubled the amount of hardware, is actually going to double. But on the other hand, it turns out that if the voltage, or rather if the frequency decreases, we can use a lower supply voltage as well, and as a result it may be possible, it is not always the case, but in general depending on the particular architecture that you have, it may be possible to reduce the supply voltage, and as a result of reducing that supply voltage we can basically bring down this overall term alpha CV squared F. The alpha is dependent on just how the architecture has been put together, we are not doing anything to change that. The capacitance in the case of a parallel implementation has doubled. The operating frequency can be made half of what it was originally, and what that means is, if I want to operate something at a lower frequency, it means I have a longer duration for the time period. It may be possible to reduce my operating supply voltage. Okay. The net result is that I can use this parallel implementation in order to bring down the total power consumed by the circuit. So even though I have more hardware present, right, because I am able to operate at a lower voltage and achieve the same throughput, right, it may be possible for me to reduce the total power consumption of the circuit.